Everything about special relativity comes from the statement that all inertial reference frames measure the same physics. From that we derive that the speed of light is constant in all inertial reference frames because Maxwell's equations are always valid. And from that fact we acknowledge that things that are moving quickly relative to us don't experience time as fast. In fact, we have this time dilation equation that says that the time of something that we observe moving quickly is the time that we experience if we're still multiplied by this factor of gamma. And gamma is, well, it's got this definition, it's 1 over the square root of 1 minus beta squared. And remember, beta is the ratio of how fast you're going to the speed of light. So if you get beta really big, really, really close to 1, gamma gets absolutely enormous. And remember that gamma then is, well, I guess the smallest that it can be is 1, and it can be all the way up to infinity. In fact, for the speed of light, gamma is infinity. Light doesn't experience time. Light literally does not experience any time. The time that the light would experience at rest is absolutely 0. So here's what I want to present. There's another deep, dark consequence of this fundamental observation that Einstein made in 1905. And that consequence is that nobody agrees on how long things are. Or in another sense, nobody agrees about distance at all. So I want you to imagine a rocket that's traveling at 87% the speed of light. Dr. Schuster, why do you like 87% the speed of light so much? Because 0.87c gives us a gamma of 2, which is nice. So then things are twice as much time or half as much time. So I want to try to figure out what's going on here with distance and time. And the thing is, I've got two situations. Let's separate them with a bold line. One situation is you're on Earth and it's down here, and you're watching a rocket, and it's going from Earth over to Alpha Centauri, which is a flaming star over here, Alpha Centauri. And everybody that you ask will say that Alpha Centauri is 4.4 light years away, which means that light takes 4.4 years to get there. You know that light, let's just do a little teaser right here. Light doesn't experience time, so light would in fact think that the Earth and Alpha Centauri are at the same place, because it would say, it took me no time at all to get there, therefore they must be at the same place because I was there, I was created at Alpha Centauri, say, and then I was destroyed at Earth, but that was the same time, so it must have been the same location. So that's a little bit interesting. There seems to be some disagreement about how far they are away, but when we look at Alpha Centauri, we think that light took 4.4 years to get there. So we say that it's 4.4 light years away, which is a pleasant distance. And if we travel in a spaceship, now I'm going to get somebody and put him in a rocket. Let's get him a seafoam green rocket. And the rocket is zooming towards... This rocket is zooming towards Alpha Centauri, and of course its velocity is 0.87 c. It's going 87% the speed of light, and it's going to take, well, let's figure out how long it's going to take to get there. I guess we could say that the time it takes to get there, careful if it's a delta t naught or a delta t, well, at any rate, delta t is going to be, I guess I'll say it's that distance, 4.4 light years divided by 0.87 c. That's going to give me the time that I calculate for it to get there. And when I do that calculation, I get 5.06. Yeah, so I get 5.06 years. That's how long. Sorry, my formatting is just terrible. It takes 5.06 years for this guy to believe that the rocket ship has made it to Alpha Centauri. The rocket ship is zooming that direction at 87% the speed of light. That's fine. That's great. But the rocket ship sees something completely differently. The rocket ship is stationary. If you get into a rocket ship, you won't think that the rocket ship is zooming around unless you have high powers of deduction. You'll probably think the rocket ship is at rest because you can still touch it the whole time during the trip. And that's a valid perspective. Who's to say that the rocket ship is moving if you're in the rocket ship? So you will say, no, the rocket ship is not moving. But what is moving? Well, Alpha Centauri is coming over. How fast is Alpha Centauri moving towards you? Seems like Alpha Centauri is going 0.87 times the speed of light. And Earth is also moving away from you, bam, at that same speed, 0.87 times the speed of light. Now that's a little bit weird. You notice that it will not take, here's the thing. if I were sitting here looking at somebody on the spaceship, that person on the spaceship is looking at a clock, and I look at his clock and I say, it's not taking him as long. Every second that I experience is taking, well, it's less than a second for this person, so their time is slower. So it doesn't take this person as long to get there. In fact, it will take that person only 2.53 years, because we know that delta t is delta t naught times gamma, and we've got gamma is 2. And in fact, I'm saying that I guess this is delta t naught would be the time of the person who's not moving in the spaceship. Delta t naught is going to be delta t. Careful now, if I start making this presented the other direction, you might get confused. But we are solving for the time of the person who's at rest relative to the two time events. And so that person there is taking much less time, because gamma is a number between 1 and infinity. So the person in the rocket ship believes that it takes them 2.53 years to get to Alpha Centauri, or to get for Alpha Centauri to get to the rocket ship, right? Because the person never thinks that they move. Also, the person on Earth will think that it took them 5.06 years. So there's a factor of 2 right there. Very interesting. How is that reconciled with the fact that this guy thinks that the rocket ship went 4.4 light years, and they both think that the speed is the same? Now that's a little bit of a problem, right? Let's investigate what that speed means. Speed is it's L naught divided by delta t. But of course that has to be the same thing as L divided by delta t naught. We've seen delta t naught. Now, let's talk a little bit about what delta t naught means. Delta t naught is the proper time. And proper time, I should make this its own slide. I will make this its own slide. Here we go. Proper time. Delta t naught. Proper time. And it's the time measured by someone who is at rest relative to the two events. At rest relative to two events. That's what proper time is. The other thing that we can know about proper time is it's also the longest possible time. Nope, shortest possible time. Ha ha ha. Shortest possible time. I find myself getting confused in this all the time. Get it? The time confuses me. So I like to keep straight what's the shortest possible time, the longest possible length, etc. Proper time is the shortest possible time. If you are moving fast relative to two events, then you will not find them at rest relative to them. So you won't find the proper time. You'll find a time that's actually much longer, because someone at those two events would observe your clock slow down, and you'll observe the proper time slowed down, so you'll see more time happening. Also, we can define L naught as the proper length. It turns out that some people don't measure the right length, but the proper length, it's not really the actual length, or maybe it is. I don't know. Which way do you want to look at this? It's all relative, isn't it, in relativity? Proper length is a very similar definition. It's the length measured if you're at rest to the object that you're measuring. So let's give names to these two people. The person on Earth I want to call Benny, and the person in the rocket ship I want to call Alice. Okay, so Benny is observing, let's see, if Alice is going from there to there, is Benny observing the proper length or the proper time for the event of Alex blasting off and then getting to Alpha Centauri? Let's see, look at these definitions. Is Benny at rest relative to the object that he's measuring? The object is this space right here. And Benny is at rest relative to Earth and relative to Alpha Centauri. So Benny measures proper length. All right? And this is, in fact, the longest possible length. And in our case, Benny measures that. Alice, on the other hand, is not at rest relative to Alpha Centauri and Earth. In fact, Alpha Centauri and Earth seem to be moving relative to her, so she can't measure the proper length. On the other hand, blasting off and landing take place at the same location for Alice. Here she is, and she is blasting off, and then a long time later, she is landing. So she's actually going to measure the proper time because she's at rest relative to the event of blasting off and landing. They take place at the same place for her. This is deeply profound and perhaps troubling, but Alice blasts off and lands at the same place from her perspective. One way to check is her nose is there with her. So clearly, she hasn't moved relative to her nose, and if she had a book right here next to her, then that book would be next to her when she landed also. She's landing and taking off at the same place. Of course, Benny doesn't think so. Benny's like, Alice, clearly you were on Earth first, and then you landed on Alpha Centauri. Oh, by the way, don't land on Alpha Centauri. It's a star. Okay, but she's at least going there. Maybe she's going to orbit it and study it or something. So Benny's going to see the proper length, and Alice is going to see the proper time. Notice that Benny's time is 5.06 years. So it's not proper because it's not the shortest possible time. Alice's time is 2.53 years. In fact, any way you slice it, that is the shortest time for any observer to observe Alice taking off and then landing. Of course, Alice herself is going to observe that at the same place, so she'll get the proper time, which is the shortest time. Now let's think about length a little bit. If you've got Benny's at rest relative to this distance. Benny thinks that the distance is 4.4 light years, and Benny has the proper distance because he's at rest relative to the distance. At rest relative to the object he's measuring. Benny is at rest. However, Alice is going to measure a shorter distance, and I'll see if I can motivate that for you. In fact, the ratio between L and L naught is very similar to the ratio between T and T naught because both of them give the speed. Benny and Alice will agree that Alice is moving at 87% the speed of light relative to Alpha Centauri. Alice just thinks Alpha Centauri is coming towards her, and Benny thinks that Alice is going towards Alpha Centauri. But the relative speed is the same, so I can set up this equation and say L naught over delta T. Whose experience is this? Who's got L naught? I forgot. Is it Benny? Yeah, Benny's got L naught, but he's got delta T. He's got the wrong time, but he's got the proper length. This is L naught. And this length right here must be L, because it's not the same length. Oh my goodness, do they not even agree on how far? I'm gonna cry! How far planets are apart from each other and stars and whatnot? Dang it! So this is Benny. And he finds the speed by L naught over delta T. And this is Alice, and she finds the speed by L. She doesn't know the proper length, but she knows the proper time. And if we just rearrange this, remember we got a relationship already between delta T and delta T naught. We know that that's equal to gamma. So I'm going to say if I solve this for delta T over delta T naught, that's going to be L over, wait a second, delta T over delta T naught is L naught over L. That's the same as delta T over delta T naught, and that's equal to gamma. So I'm going to take this equation right here, sorry for the clutter, and I'm going to go up there with it a little bit, and I'm going to say that L, that is contracted length, is equal to L naught divided by gamma. Remember, gamma is bounded between 1 and infinity, so the length that Alice observes is less than the actual length between Alpha Centauri and Earth. And so let's figure out what it is. We're going to have to divide by gamma. So in fact, Alice believes that she has gone only 2.2 light years. Dang! Would it still take her 2.53 years? Yeah, it would. You tried dividing that. It would. It works out. It is awesome and also frightening. Some results will be discussed in the next video. Everything about special relativity comes from the statement that all inertial reference frames measure the same physics. From that, we derive that the speed of light is constant in all inertial reference frames because Maxwell's equations are always valid. And from that fact, we acknowledge that things that are moving quickly relative to us don't experience time as fast. In fact, if you get beta really big, really close to 1, gamma gets absolutely enormous. And remember that gamma then is, well, I guess guess the smallest that it can be is 1, and it can be all the way up to infinity. In fact, for the speed of light, gamma is infinity. Light doesn't experience time. Light literally does not experience any time. The time that the light would experience at rest is absolutely 0. So here's what I want to present. There's another deep, dark consequence of this fundamental observation that Einstein made in 1905. And that consequence is that nobody agrees on how long things are. Or in another sense, nobody agrees about distance at all. So I want you to imagine a rocket that's traveling at 87%. In fact, we have this time dilation equation that says that the time of something that we observe moving quickly is the time that we experience if we're still, multiplied by this factor of gamma. And gamma is, well, it's got this definition, it's 1 over the square root of 1 minus beta squared. And remember, beta is the ratio of how fast you're going to the speed of light. So at the speed of light. Dr. Schuster, why do you like 87% the speed of light so much? Because 0.87c gives us a gamma of 2, which is nice. So then things are twice as much time or half as much time. So I want to try to figure out what's going on here with distance and time. And the thing is, I've got two situations. Let's